Welcome back, learners. Today, we're going to be taking a deep dive into the world of resin photopolymerization in dentistry.
Oh, very cool.
You sent over a whole stack of research papers,
Yeah.
and it looks like as a graduate level student, you're really trying to solidify your understanding of
Right.
this whole area.
It's definitely a fascinating area and it's constantly evolving.
For sure, for sure.
Always new things coming out, new materials, new techniques.
Absolutely.
Yeah.
So let's start with the fundamentals. Like, how do these resins transform from that kind of moldable paste,
Yeah.
into a hard, durable filling?
Yeah. Well, it all comes down to
Okay.
light activated chemistry.
Yeah.
Essentially, we're taking a collection of monomers, which are the building blocks of the resin,
Okay.
and we're using light to trigger a chain reaction
Right.
that links them together into long chains called polymers.
So it's like we're constructing something from tiny molecular Legos,
Yeah.
but instead of snapping them together, with our hands, we're using photons to do the work.
That's a great analogy. Yeah.
Now, one of the most common monomers that I saw in the research
Yeah.
is bis-GMA.
Bis-GMA. Yeah.
What can you tell me about that?
So bis-GMA, that's kind of our workhorse monomer, you could say.
Okay.
It's known for its strength and durability.
So it's like the foundation of our molecular structure.
Yeah, you can think of it that way. Yeah.
But to kickstart the whole process, don't we need some kind of catalyst
Yes, we do.
to get things going?
We need a photoinitiator.
Okay, photoinitiator.
And so what that is, it's a molecule that absorbs light energy
Okay.
and uses it to generate free radicals.
Okay.
And those are highly reactive species that start the chain reaction of the polymerization.
Gotcha. So they're like the foreman of the construction crew.
Yeah.
Getting everything.
Yeah, that's a good way to think about it.
So one that I saw a lot is called camphorquinone,
Camphorquinone, yeah.
and it's activated by blue light.
Yes, very commonly used photoinitiator activated by blue light.
So the camphorquinone is like the spark that
Right.
ignites the whole process.
Yep, sets off the whole chain reaction.
And traditionally, acrylics used for dentures, I think, relied on heat to activate the whole process.
You're exactly right, yeah.
And those are called heat-cured acrylics.
Heat-cured acrylics, that's right.
But with the advent of light-cured resins, we've got much greater control now over the curing process.
Yeah, it's definitely a more controlled and precise approach.
Right.
It allows dentists to really kind of fine-tune the setting time and the shape of the filling.
And I imagine that has had a pretty significant impact on, clinical practice.
Oh, absolutely. Yeah, it's really revolutionized the way that we
Yeah.
approach restorative dentistry.
Now, one of the papers that you sent over talked a lot about shrinkage
Yeah.
as a major concern during polymerization.
Shrinkage is a big one, yeah.
So can you tell me a little bit more about that?
Yeah, so as those monomers link together to form the polymers,
Okay.
they occupy a slightly smaller volume, which can lead to gaps between the filling and the tooth structure.
Oh, wow.
And that's something that we really want to avoid.
So it's a microscopic phenomenon,
Yeah.
but with potentially, larger consequences.
Yeah, exactly. You got it.
Now, how do researchers mitigate that shrinkage?
Yeah. So there's a lot of research going on in this area,
Okay.
trying to develop new materials and techniques to minimize it.
Right.
One approach is to incorporate fillers
Fillers.
into the resin matrix.
Okay.
So you can kind of think of it as adding reinforcements to concrete.
Gotcha. So like rebar
Exactly. Yeah.
reinforcing the concrete.
Yeah.
So the fillers are doing the same thing.
They're providing strength and stability
Okay.
to the resin.
Now, what can you tell me about the different types of fillers?
So there's a variety of fillers available.
Okay.
They come in different sizes and shapes.
Right.
And each type has its own unique properties.
Okay.
For example, you have microfills,
Okay.
which are very tiny particles.
Right.
They create a very smooth surface.
Okay.
So they're ideal for anterior restorations,
That's-
where aesthetics are really important.
Okay.
And then you have hybrid fillers,
Uh-huh.
which combine different particle sizes
Okay.
to achieve kind of a balance of strength and aesthetics.
So it's all about picking the right filler for the right clinical situation.
Yeah, exactly right.
And that's kind of a theme that I'm noticing here is that customization and precision are really at the heart of this whole process.
You're absolutely right. It's not a one-size-fits-all approach.
Right.
Dentists have to carefully consider, all these different factors, the
Uh-huh.
monomer, the photoinitiator, the filler,
Right.
even the light source that they're using.
Speaking of the light source,
Yeah,
I know that early light-cured resins relied on UV light,
that's right.
but I'm guessing there were some issues with that.
Yeah, UV light does have some drawbacks.
Okay.
It has a limited depth of cure,
Okay.
meaning it can't penetrate very deep into the resin.
Okay.
And there's also a risk of tissue damage with prolonged exposure.
Yeah, that makes sense. So it's like we can't just blast it with a ton of UV light
Right, exactly.
to make sure that it cures because there could be some negative
Mm.
consequences.
Yeah, too much of a good thing can be a bad thing.
Right, right.
So nowadays, we primarily use visible blue light.
Okay.
It's much safer, it's more efficient,
Okay.
and it's compatible with a wider range of photoinitiators.
So blue light's kind of the gold standard.
It's the go-to for most dental applications
Yeah.
these days, yeah.
Okay.
And it's really opened up new possibilities in
Right.
terms of the types of resins
Yeah.
and the curing techniques that we can use.
Now, BIS-GMA, yeah, it's kind of the workhorse,
Yeah.
but I know that there's a lot of research going on to find other monomers
Yes.
to address some of its limitations.
Yes, right.
So what are some of those limitations?
So one of the limitations of this GMA is that it can absorb water over time
Okay.
from the oral environment,
Right.
and that can lead to softening and degradation of the material.
Gotcha. So it's not ideal.
Yeah, it's something that we'd like to improve upon.
Okay.
So researchers are exploring alternative monomers,
Right.
such as FIT852,
Okay.
which is a urethane-based monomer,
Okay.
and it's much more hydrophobic,
Okay.
meaning that it repels water.
Gotcha. So it's like a water-resistant shield,
Yeah, you can think of it that way.
protecting it from the harsh environment of the mouth.
Exactly.
Now, what about viscosity?
Yeah, so another limitation of BIS-GMA
Right.
is that it has a relatively high viscosity,
Okay.
meaning it's kind of thick and sticky,
Gotcha.
which can make it a little challenging to manipulate
Yeah.
and adapt to the contours of the tooth.
Yeah, I can imagine that would be pretty tricky.
Yeah, it can be a bit finicky.
So what are researchers doing to kind of address that?
Well, they're looking at monomers like bis-IMA,
Vicine.
which has ether linkages
Okay.
that give it greater flexibility.
So it's a little bit more pliable,
Exactly.
easier to work with.
That's the idea.
So it sounds like the quest for the ideal monomer is ongoing.
It definitely is an ongoing process. Yeah.
Always room for improvement.
Always, always.
Now with all these new materials being developed, we have to make sure that they're biocompatible.
Absolutely.
That's a top priority,
We want to make sure that they're safe for use in the human body.
right? We don't want to be introducing any new problems.
Right. And one concern that's been raised in the past is the potential toxicity of bisphenol A.
BPA.
Yes.
BPA.
That's been a hot topic.
It has. So how do dental resins address that concern?
So while BPA is a component of some dental resins,
Okay.
the amount that's actually released is extremely low.
Okay.
And it's generally considered to be safe.
Okay.
But of course, dentists follow very strict protocols
Right.
to minimize exposure to uncured resins.
Right.
And they use protective measures during the light curing process.
Well, it's good to know that there are those safeguards in place.
Yes, safety is paramount.
So we've covered the basic building blocks of dental resins.
Yeah.
The monomers, the photoinitiators, the fillers.
Mm-hmm.
And we've talked about the importance of the light source
Right.
and the ongoing search for new and improved materials.
Yep.
But there's still so much more to explore.
There is a lot more to this. Yeah.
So that's what we're going to be doing in the next part of our deep dive.
Great.
We're going to delve into the polymerization process itself.
Okay.
We'll talk about the degree of conversion,
Mm-hmm.
the oxygen inhibition layer,
Right.
and post-cure polymerization.
Sounds good.
So stay tuned, learners. We'll be back after a short break
Hurry.
to continue our exploration of the fascinating world of resin photopolymerization.
Looking forward to it. So let's dive a little bit deeper into the heart of resin photopolymerization.
Okay.
And that's the polymerization process itself.
All right, so this is where all the molecular magic happens, right?
Yeah. This is where it all comes together.
Transforming those liquid monomers into a solid, durable material.
Right.
What are the key stages in this process?
Okay. Well, it starts with our photoinitiator,
Okay.
camphorquinone,
Right.
absorbing that blue light
Uh-huh.
and getting excited to a higher energy level.
Okay.
Then this energized camphorquinone interacts with an enantiomine co-initiator,
Okay.
and that generates free radicals.
Okay.
So you can think of these free radicals as highly reactive,
Okay.
eager beavers ready to start the polymerization party.
So the camphorquinone is like the DJ spinning the tunes,
I like that analogy.
and the enagamy is like the hype man,
Yeah, getting the party started.
getting everybody pumped up.
That's a good way to think about it.
Okay, so we got the free radicals. What happens next?
So then these free radicals, they run into our bis-GMA monomers,
Right.
and they initiate a chain reaction.
Okay.
So one free radical will react with a monomer,
Okay.
create a new larger free radical, and that will react with another monomer, and so on and so forth.
So it's like a molecular conga line?
It is a molecular conga line.
It's just getting longer and longer.
Growing and growing until you have the solid material.
And that's how we end up with that solid restoration.
Right.
Okay, so we've got the light triggering the process,
Mm-hmm.
but does the polymerization just stop when we turn the light off?
That's a great question, and actually it doesn't completely stop.
Okay.
There's something called the Trommsdorff effect.
The Trommsdorff effect.
Or sometimes it's called the gel effect.
Okay.
What happens is, as the polymerization progresses and the resin transitions from a liquid to a more viscous gel,
So,
the movement of those growing polymer chains becomes restricted.
so they're kind of getting crowded.
They're getting crowded, yeah, they're bumping into each other.
Okay.
And so it makes it harder for them to find each other and terminate the reaction.
Oh, so they can't escape.
Exactly. So even after the light is off,
Okay.
the remaining free radicals, they can continue to react with available monomers
Okay.
and increase the degree of conversion.
So that's the percentage of monomers that have actually reacted to form polymers.
That's right.
So the party keeps going even after the main lights have gone out.
Exactly, the after party of polymerization.
So that's good in a way, right?
It is, yeah, because it contributes to the final strength and stability of the restoration.
Okay, so we have the Trommsdorff effect, we got the after party going on.
Yeah.
But there's something else that dentists have to be mindful of
Yes.
during this curing process.
Right.
And that is the oxygen inhibition layer.
Yes, the oxygen inhibition layer.
Can you tell me more about that?
So oxygen in the air,
Uh-huh.
it can actually interfere with the polymerization process at the surface of the resin.
How does it do that?
So oxygen molecules are really good at reacting with free radicals.
Okay.
They basically scavenge them up
Okay.
and prevent them from participating in the polymerization.
So they're like little Pac-Man ghosts
Yeah, gobbling up those free radicals.
running around and eating them all up.
Exactly. And because oxygen is most abundant at the surface of the resin,
Uh-huh.
that's where you get this inhibition effect.
So we end up with this uncured or partially cured layer on the surface.
That's right.
So what can dentists do about that?
Well, fortunately, there are a few tricks
Okay, good.
that they can use.
Right.
One common technique is to use a physical barrier,
Great.
like a matrix strip,
Oh.
to block oxygen from reaching the resin surface during curing.
So it's like putting up a fence
Exactly. Yeah, creating a little protected area.
to keep those oxygen molecules out.
Keep them away from those free radicals.
Okay. Are there any other strategies that they can use?
Yeah, they can also use special barrier layer products.
Okay.
And these are typically liquids,
Okay.
like glycerol,
Uh-huh.
that are applied to the resin surface before curing.
Okay.
And they create this temporary oxygen-resistant layer.
So it's like a suit of armor
Yeah, like a protective shield.
protecting those vulnerable monomers.
Exactly.
Okay, that makes sense. But what happens after the filling is cured
Yeah,
and the matrix strip is removed?
right.
Does that oxygen inhibition layer just stay there?
Well, not necessarily.
Okay.
So once the main curing light is off,
Uh-huh.
that oxygen inhibition layer will gradually harden as the remaining free radicals react with any available monomers.
So it's like a delayed reaction.
It's a slower process,
Okay.
but it does contribute to what we call post-cure polymerization.
Okay, so the party's not over.
The party continues
It just keeps
a
going
little bit slower,
at a slower pace.
but it's still happening.
So that's really fascinating.
Yeah,
That it's such a dynamic process.
it is.
It doesn't just end when the light goes off.
Right. It continues for a while.
Okay, so with all this complexity,
Yeah.
why are resin-based fillings so popular?
That's a good question.
Wouldn't it be easier to stick with the old-fashioned metal fillings?
Well, metal fillings, they do have their advantages.
Okay,
They're durable, they're
Yeah.
cost effective,
right.
but they also have some limitations.
Okay,
Aesthetically, they're not as appealing,
right.
especially in the front teeth.
Yeah, they're very visible.
They can be very noticeable,
Yeah,
and they can also sometimes cause sensitivity to hot and cold. So resin-based fillings, they offer a more natural-looking solution.
okay,
They can be color-matched to the tooth,
right.
so they blend in really well,
Yeah.
and they don't conduct heat as readily as metal,
Right.
so you're less likely to experience sensitivity.
So it sounds like patient comfort
Yeah,
is a
yeah,
big factor,
absolutely.
and aesthetics.
Patient comfort and aesthetics are key.
So what's next for resin photopolymerization?
Well, researchers are always looking for ways to improve.
Okay.
One area of active development is bioactive resins.
Bioactive resins.
Yeah, so these are resins that are designed to interact with the surrounding tooth structure
Okay.
in a beneficial way.
Okay.
So, unlike traditional resins,
Uh-huh.
which are basically inert
Hmm.
materials,
Uh-huh.
bioactive resins can release ions
Okay.
like calcium and phosphate,
Okay.
which are essential for tooth remineralization.
So it's not just building the structure, it's also kind of helping to keep the tooth healthy.
That's a great way to put it, yeah.
Wow. So are bioactive resins actually being used yet?
There are a few bioactive resin-based materials available,
Okay.
and research in this area is really exploding.
It's really interesting to think about all the possibilities.
It is, yeah, it's a very exciting area.
Now let's talk about toxicity,
Okay,
because that's something that we really need to consider.
absolutely.
One of the papers that you sent over talked about the cytotoxicity and
All
genotoxicity
right.
of different resin components.
Yeah, those are important factors to consider.
So can you kind of break down what those terms mean?
Yeah, so cytotoxicity refers to the ability of a substance to damage or kill cells.
Okay.
Basically, how toxic it is to living tissue.
And genotoxicity.
Genotoxicity is the ability of a substance to damage DNA.
Gotcha. So we want to make sure that these materials aren't causing mutations or damaging our cells.
Exactly. That's why researchers do all these tests to make sure that these materials are safe.
And one of the papers you sent over actually compared the cytotoxicity and genotoxicity
Right.
of several different monomers and photoinitiators.
They use some pretty sophisticated tests.
Yeah, like what kind of tests?
Well, one is called the MTT assay.
The MTT assay.
Yeah, it's a way to measure cell viability.
Okay,
So basically, how many cells are alive and well after being exposed to the substance?
gotcha.
And then there's the COMET assay.
The COMET assay, what is that?
So that's a really cool technique
Okay.
for visualizing DNA damage.
Wow.
So they subject the cells to an electric field.
Okay.
And if the DNA is damaged, it fragments
Uh-huh.
and it migrates away from the cell body,
Okay.
creating kind of a comet-like tail.
So they can actually see the
You
damage.
can actually see it under a microscope.
That's incredible.
It's pretty amazing, yeah.
Now, what about the interactions between different resin components?
That's another important area of research because sometimes you get unexpected results
Okay.
when you combine different things.
Like what?
Well, for example, in one study, they found that bis-GMA,
Okay.
when it was combined with a photoinitiator called TPO, it actually had a synergistic effect.
Synergistic, what does that mean?
It means the combination was more toxic
I know.
than either component alone.
Okay, so 1 + 1 doesn't always equal 2?
Sometimes it equals 3 or
Okay.
even more.
Wow.
But then they also found antagonistic effects.
Antagonistic.
Yeah, so that's the opposite.
Okay.
The combination is less toxic than the individual components.
Wow, so it's really complex.
It is very complex.
So we have these new monomers.
Yes.
Like FIT852 and BisMA.
Right.
But are there any other alternatives to bis-GMA?
There are a few others out there.
Okay.
One that's gaining a lot of attention is silyarene.
Silyarene.
Yeah.
I haven't heard of that one.
It's a really interesting monomer.
Okay.
It polymerizes through a ring opening process
Okay.
rather than the traditional free radical mechanism.
So how does that work?
So instead of free radicals initiating the chain reaction,
Uh-huh.
the silyarene molecules, they open up their ring structures
Okay.
and they link together in a more controlled manner.
So it's a different kind of party.
It's a different kind of party, yeah.
A different way of getting those monomers to link up.
Exactly.
So what are the advantages of that?
Well, one of the big advantages is that it has lower shrinkage stress
Okay, that's good.
and reduced water sorption
Oh,
compared to bis-GMA.
so that's 2 big wins.
Two big wins, yeah.
Are there any drawbacks?
There are a few.
Okay.
It can be a bit more technique sensitive to work with,
Okay.
and it may require slightly longer curing times.
Gotcha.
But overall, it's a very promising alternative.
Especially in those cases where shrinkage is a big concern.
Exactly.
Now, one of the papers that you send over
Yeah.
talked about triplet state photoinitiator systems.
Oh, yeah. Those are really cool.
What can you tell me about those?
So they offer a different way to trigger the polymerization.
Okay.
It's a more indirect mechanism
Right.
where a molecule absorbs light
Uh-huh.
and it transitions to a higher energy level
Okay.
called a triplet state.
Okay.
And then this excited molecule transfers its energy to another molecule,
Okay.
which then initiates the polymerization.
So it's like a relay race,
It is like a relay race, yeah.
passing the energy along.
Exactly, passing the baton.
Okay. So what's the advantage of using that system?
Well, one of the key advantages is that it allows us to use longer wavelengths of light,
Okay.
and those can penetrate deeper into the resin
Oh, wow.
and into the tooth structure.
Oh, yeah.
So it's especially beneficial for curing larger restorations
Gotcha.
or restorations that are in hard to reach areas.
So we've got all this new research going on, all these new
Yeah,
advancements.
it's a really dynamic field.
And as a graduate level student, I mean, you're really at the forefront of all this.
It's exciting to be a part of it.
So on that note, I think we'll conclude part 2
Okay,
of our deep dive into resin photopolymerization.
sounds good.
We've talked about, the mechanisms of polymerization,
Yeah.
the different materials,
Huh.
the bioactive resins,
Right.
and the new photoinitiator systems.
A lot to cover.
And we'll continue our exploration
Right.
in part 3, where we're going to talk about the practical considerations of resin photopolymerization.
Looking forward to it.
All right, so welcome back to our deep dive into resin photopolymerization. We've really explored the building blocks of these materials, to the intricacies of that whole polymerization process, and even taken a peek into the future, with bioactive resins and things like that.
Yeah, it's been quite a journey.
But now let's shift gears a little bit
Okay.
and talk about some of the practical considerations,
Yeah, all right.
when it comes to actually using these materials.
That sounds good.
So let's put on our dentist hats for a minute
Okay.
and think about, what are the things that really influence the success of a resin-based restoration?
All right.
And one that jumps out at me right away is curing efficiency.
That's a big one.
So what determines, how well a resin cures?
So curing efficiency, or the degree of conversion, as it's sometimes called,
Yeah.
is influenced by a lot of different factors.
Okay.
You've got light intensity, exposure time,
Okay.
the wavelength of the curing light,
Right.
even the composition of the resin itself.
So light intensity, I'm assuming the higher the intensity, the faster, more complete the cure.
Generally, yes.
But there's a catch.
Okay, there's always a catch, right?
Yeah, if the intensity is too high,
Okay.
you can generate a lot of heat,
Okay.
and that can damage the tooth
Right.
or even the resin itself.
Well, so you got to find that sweet spot.
Yeah, it's all about finding the right balance.
Okay, now what about the wavelength of the curing light? We talked about blue light being the most common.
Right, blue light is the go-to.
But are all blue lights created equal?
Not exactly.
Okay.
Different wavelengths within that blue spectrum can affect how well the photoinitiator works
Okay.
and how deep the light can penetrate.
So it's not just as simple as, point a blue light at it and we're good to go.
It's a little more nuanced than that.
All right, well, one of the papers you sent me talked about the importance of using proper light curing techniques. Yeah, there's definitely a technique to it.
So what are some of the things that dentists need to keep in mind to ensure that they're getting a thorough cure?
So one thing is the distance between the light tip and the resin.
Okay.
The intensity of light decreases pretty dramatically with distance.
So the closer, the better.
The closer, the better. Yeah.
Okay.
You want to be as close as you can without actually touching the resin.
Okay.
And then the angle of the light is also important.
Right.
Ideally, you want the light to be shining directly onto the surface of the resin.
Okay. Perpendicular.
Yeah, perpendicular. So you get nice, even coverage.
So it's not just about proximity. It's also about precision.
That's right.
Okay. Now, I've heard about something called incremental curing.
Yes.
Can you explain what that is?
So that's a technique where you cure the resin in layers
Okay.
rather than all at once.
And why do we do that?
Well, as the resin polymerizes, it shrinks.
Right.
And if you cure a large volume all at once, that shrinkage can create a lot of stress,
Okay.
which can lead to cracks or gaps.
So we're kind of breaking it down into smaller, more manageable chunks
Exactly.
to minimize that stress.
Right.
Now, even with the best techniques, can we ever achieve 100% polymerization?
Well, that's the goal.
Okay.
But in reality, it's very difficult to achieve 100% conversion.
So there's always room for improvement.
Always, always.
All right. Well, I think this has been an incredibly enlightening deep dive
I agree.
into the world of resin photopolymerization.
It's a fascinating area.
It really is. And we've covered so much ground,
We have.
from the basic building blocks of these materials to the complexities of the curing process and the amazing advancements that are happening all the time.
It's an exciting time to be in dentistry.
And for our listeners, we hope this deep dive has given you a much deeper appreciation for the science that goes into those tooth-colored fillings
Absolutely.
that are so common these days.
And hopefully it sparked some curiosity
For sure.
to learn even more.
So until next time, keep those smiles shining.
And those minds curious.